one of the most destructive kinds of waves that we ever see in the oceans, which is actually confused as a tidal wave, because by definition a tidal wave is an increase in the ocean level followed by a decrease in the ocean level and vice versa. And basically that's what happens during a tsunami, and where the tsunami actually has a wave that increases so much that takes over the land, right? But right before the tsunami happens, typically the wave, the shoreline retreats. And then after the tsunami happens, it actually retreats back again. So it does look like a tide, but it's a tide that happens kind of fast to be an actual tide. Because tides, each tidal fluctuation, like we're going to talk about, well, it depends on the place, but typically tidal fluctuations happen every 12 hours or so. And tsunamis will happen in matters of minutes or hours. So we're not talking about tidal waves. Now, although they're confused with tidal waves, tsunamis are actually oceanic seismic waves. And they're considered what we call the long period waves, or waves caused by large disturbances of the ocean, all right, which are the only negative force that these waves have to beat is the Coriolis force. Basically, gravity is not going to be stopping these waves. Surface tension is definitely not going to be stopping these waves. The only thing that can mess with these waves is the Coriolis force. You know, those bulges that happen at the open ocean are going to be messing up with these waves. We talked about this when we talk about types of waves. Go back and watch that video if you don't remember that. Now, long period waves, as a definition, are weak waves. So hold on a second, Mr. Lima. Are you telling me that tsunamis are weak waves? Yes. Tsunamis are actually weak waves. Tsunamis do not have a lot of power in terms of wave motion. Because when you think of a wave, you think of something that is moving up and down and up and down and up and down. And when you think about wave energy, that's usually shown as wave height and speed or frequency. Okay, so we're talking about a very strong wave. We're talking about something that has a very short wavelength, extremely high frequencies, and a really large amplitudes. That is not the description of a tsunami. Now, a typical wave of the ocean has a lot more energy than a tsunami ever does. So how can a tsunami be causing so much damage? I know it seems counterintuitive. Yes, the tsunamis do hit the beach with a massive amount of power. But if you consider the size of the tsunami wave, that is not a strong wave. The tsunami wave, when you see the wave coming, it is actually the size of an entire ocean basin almost. You can have one wave come and another one come 20, 30 minutes later, maybe hours later. So we're talking about a wave period which is so high and a frequency which is so low that very rarely these waves are hitting you, that you're talking about a very weak wave. Now, although it's a very weak wave, it comes in very strong pulses. In other words, each time a crest hits you, each crest carries a lot of energy per crest, even though the whole wave has very little energy, because that energy is spread out into an enormous piece of the ocean. So to put that in perspective, it would be something like saying, which wave has more energy? A wave that has this much energy, right? So I'm doing back and forth like that, or a wave that has the same amount of energy but spread out like that. Well, that wave has a lot more energy because it's hitting you more often, it has a shorter wave period, and a decent amplitude. Well, this wave here seems to be more energy, but it's not, because the entire energy is spread out for this entire region, so it's not a strong wave. That's the idea behind a tsunami. However, each pulse, each crest that hits you with a lot more power than each of these crests hits you. So it feels like the wave is more powerful. The wave is weaker. The pulses are stronger, if that makes any sense. All right? Now, what's happening with the tsunami is that it's carrying a massive wall of water extremely fast through the ocean. And so even though it has a very long wave period and a very, very big frequency, no, short frequency, that means that a very little waves hits you per second. It will actually take hours between each wave hitting you. It still has a lot of power because it's coming through with a lot of speed. So each pulse comes very, very fast. Now, if you were to compare the amplitude of a tsunami wave with a normal wave, it would be something like this. A normal wave would be like this big, and a tsunami wave would be like that big. So we're talking about the fact that that's another misconception about tsunamis. Okay? Tsunamis are not large waves, all right, in terms of height. The wave height of tsunamis is very, very small. When these normal waves or gravity waves or the waves that are caused by a wind are traveling through the oceans, some of those gravity waves can get like to 50 meters of height out there in the open water. There's been cases of rogue waves or solitary waves which have gotten that big because it's all the wave energy concentrated in one pulse. All right? And then you also have normal gravity waves which can get to 20, 30 meters during a storm. All right? But the tsunami waves are these tiny, minuscule waves. So if you were in the open ocean and a tsunami were to go by you, you might not even feel it. It'll be like, whoa, did you just feel that? Well, I felt it, but it was very sudden, very fast. It barely touched me, and all I felt was maybe 1 meter up. So it's like you were going to go up and down 1 meter in a split second, because the wave is traveling very fast, but not very high. So it's not like you're going to go up 20 meters in a second. You go up 1 meter in a second. So we're not talking about a very strong wave. We're talking about a fast-moving pulse, right? Now, the thing about tsunamis is that once this pulse hits the beach, and you can see that happening over here, it comes in with such speed and so much power per pulse that it creates ginormous breaks and ginormous cusps and tremendously huge crests. So what we're talking about here is that the wave comes so fast. And remember that when waves hit the shoreline, they slow down, but they gain height. So for everything that the wave slows down, it gains in height. That's a normal wave we're talking about. But since tsunami waves are traveling so fast, it will gain so much height that it will be enormous. Which means tsunami waves are very short, something like 1 meter when they're in the open ocean. But then once they finally hit the beach, all the speed they have converts into height, and that basically gets 10 times whatever they were before. So if you have a tsunami wave in the open ocean that's 3 meters, that's going to be a 30-meter wave or a 90-foot wave up hitting the beach. It's extremely large, but only when it hits the beach. Also, if the normal cusp, which is actually, you know, when the wave hits the beach, it looks like those little hills that's hitting the beach. If the normal cusp of a wave is tiny like this, a tsunami cusp will be maybe 40 times bigger than that. So one cusp can take over an entire island. So imagine when you look at the beach and you see this. See, this is a cusp right there. You know, one cusp of the tsunami wave. This entire thing you see in this picture is just one cusp. Imagine the entire pulse if you look at it. So the thing about tsunami waves is they're very large and moving very fast. And so what they had in speed, they gain in height and cusp size as they hit the beach. Which means what you're essentially getting is not so much in energy, in power, but you are getting in volume of water that's massively and very fast going over the beach. And it's going to be a while before this wave slows down. Remember, a normal breaker will slow down fast as it hits the beach, but this tsunami wave will collapse, certainly, way before they hit the beach. So this large wave here will collapse way before it actually hits the continent. But even after it collapses, it keeps going into the continent for miles into the continent, flooding the continent. And that is what creates the destruction of the tsunami. So, what causes tsunamis? What actually causes tsunamis? Okay? So here's you see the things we were talking about. It makes a ginormous wave as it actually approaches the beach. And that happens because all the speed the tsunami had translates into height as it approaches the beach. And it comes with so much power that it quickly runs over the land with a wall of water. And that is what actually creates a normal tsunami. So wind waves usually come in without flooding higher areas because they're flowing in a circular pattern, right? Which cause the waves to crash and all of that. Tsunami waves are flowing so fast and circulating so little that it looks like the water is actually flowing straight. And so it slows down even less and it grows up even more and creates a wall of water. So when you think of a tsunami, when you see those videos in the movies that you see that's ginormous breaker coming through and taking over the land, that's not a real tsunami. That doesn't exist. That's a ginormous wind wave. And those things don't really happen because, remember, waves, when they get large, they collapse under their own weight. So those things don't really happen. A tsunami wave is more like a wall of water that is coming all at once, and gaining height as it approaches the beach. All the speed gets converted to height. But you don't get so much of a breaker the way you would in a normal circulating wave. Instead, you get an ever-rising wall of water that very quickly takes over the land, and it will take a while for it to slow down. Two things that will cause tsunamis is earthquakes. Whenever an earthquake happens in the open ocean, maybe in that subduction zone that's between the continental shelf and the oceanic shelf, it will basically cause a lot of friction there, and when that friction gets released and it gets elastic rebound, the same rebound that caused the earthquake makes the water suddenly move upwards and create the tsunami wave. So one of the major causes for tsunamis are earthquakes. The earthquake creates a pulse that then travels towards the beach and quickly takes over the land. And see that happening there. The oscillation that's set off at deep water travels like upwards and creates a shock wave, then moves the surface of the water very quickly and sends a pulse of enormous speed, which gets converted into height and takes a very long time to slow down, and that's why it takes over the land. Now, tsunamis can also happen because of turbidity currents or underwater landslides, like seen here on the top left, because of massive meteor impacts or because of volcanic eruptions that happen in the water. So these are other causes for tsunami actions, but the majority of tsunamis are usually earthquakes. But if a continental crust were to collapse in Africa, for example, a massive tsunami would be caused coming towards the Americas. And obviously, if a meteor explosion happened or underwater eruption happened, those things also create shock waves, which translate into tsunamis or long period waves. Okay? Now, the reason why tsunamis cause so much destruction is because of the massive amount of wall of water that quickly takes over the land. So you're going to get a lot of flooding, a lot of structural damage, a lot of things like that. And really, to actually get a good idea about the way the tsunami looks, you need to actually watch videos about this, and I have playlists about it on my YouTube channel as well. Okay? Now, tsunamis actually, look at the size of a cusp of a tsunami wave. This entire thing is one large tsunami wave. So we're talking about ginormous tsunami waves, and you can see how it travels very fast. Something that happens in Japan will travel all the way to South America in only 21 hours. So this is going at jet speeds over the ocean surface, and that's what's spreading very quickly, and that's why it gets so much power per pulse. But each wave will hit hours apart or minutes apart, or that's why it has such a large wave. Now, you see these little dots? What those things are tidal gauges. And they basically are designed to measure the rise of a sudden rise in the sea level to see if the tsunami is coming. And the way it basically works is that a buoy, basically, or a tidal gauge, or basically a device at the bottom of the ocean, communicates with the buoy, who also communicates with the satellite. And these satellites are interacting with several buoys all over the earth. And whenever they detect that the ocean level went higher, either because the distance between the buoy and the satellite went down, or because the distance between the buoy and the floor went up, you realize that this buoy is traveling higher in a split second. And so you know it's probably a massive tsunami wave that's coming. And you can use that to create evacuation signals, which can tell people to go to higher ground and leave their houses and protect themselves from the massive ocean water, wall of water that's coming. So usually the first thing that happens in order to detect a tsunami that's coming is the detection of the actual cause. Say, I know a landslide happened, I know a volcanic eruption happened, I know we got hit by an asteroid, or I know there was a massive earthquake. Then they activate and pay attention to the gauges. If they see a sudden rise in the gauges after a major event like that, that's when the tsunami warning goes up. So the first warning comes after a major cause. The second warning comes after you notice that the gauge is registering a sudden increase. And then at that point, people really need to vacate and go to higher ground in order to protect themselves from being destroyed by the tsunami. So, and another thing you can do too is that right before the tsunami actually comes, the water level tends to go backwards. And you see here, this is the area right here where the beach is supposed to be at. And you see how far back the water is. Again, the same thing here. Look, you see the boat in the middle of the land. You see how the beach is supposed to be up here, but it's actually here. You see how it's supposed to be up there, but look what the water is. So the water tends to actually move backwards before it moves forwards. And that's another way you can tell the tsunami is coming. Putting all three together, you can actually create a very decent warning to make you avoid being hit by these massive tsunami waves, which cause so much destruction and death. Alright? So I hope you learned things about tsunamis, and make sure you watch the videos as well. See you on the next lecture video.